right, here we go. We're going to start talking about exponential functions. Okay. Now, these are some Desmos graphs I've created, and an exponential function is really goes by a real simple name. You know, it's of the form f of x equals a to the x, a to the x. Okay, so here it is, a to the x. Of course, the exponent is the unknown here. So that's what makes this kind of unique. So here we go. We're looking at 2 to the x. 2 to the x. Here's our graph of 2 to the x right there. Okay. Here's our graph of 3 to the x. Okay. Here's our graph of 5 to the x. Here's our graph of 8 to the x. All right. And of course, what you can see is the graphs are all very much the same shape. Here's a graph of 10 to the x, okay? All very much the same shape, okay? And they're characterized by really two things, okay? An intercept right there at 1, okay? Why? Because 2 to the first power, okay, or rather 2 to the 0 power, which is at the x-intercept, the y-intercept when x equals 0. 2 to the 0 power is 1. 3 to the 0 power is 1. 5 to the 0 power is 1, right? 10 to the 0 power is 1. So all exponential functions of this variety, y equals a to the x, will have that y-intercept at 1. Then in addition, they have the asymptote. So let's look at the 2 to the x graph, okay? If I said 2 to the -1, x being -1, then I have a value here of 1/2. If I say 2 to the -2, I have a value here of 1/4, because 2 to the -2 is a quarter. If I say I have a value of -3, then I have 1/8 right here. A -4 would give me 1/16. So we can see that the graph is approaching the x-axis, that is the limit as x moves towards negative infinity is becoming closer and closer to 0. All right, so we have an asymptote on the negative x-axis, but then we have the thing just swooping up and just getting larger and larger. Just if we go out to 8, we're all the way up to what? Well, we're at 2 to the 8th here. 2 to the 8th is all the way up to, what's that, 256? So that's way off. Even up at 2 to the 4th, we're up to 16. So you can see that this thing, the rate of change in which is kind of measures how quickly it's growing. Okay, it just grows very rapidly. And of course, if we get you know up to 3 to the x, then of course it's growing even more rapidly. The rate of change is growing even more rapidly. 5 to the x, so we can see how quickly that thing grows, okay? So in essence, we find that nothing outruns an exponential function. Nothing outruns an exponential function. So other thing that's worth noting is that we can see that the base here can be most any value, okay? 2, 2.1, 2.5, 2.6, any value in fact. In fact, we'll even see with sometimes you might have a base that's irrational, like pi, okay, or radical 2. It's all possible, okay? But all we're looking at is an intercept and an asymptote, which pretty much define this function, okay? Now we're going to talk about some of those things, okay, in the presentation here, the PowerPoint presentation. So let's take a look at that, okay, and talk about that for a little bit. So the exponential functions that we've been talking about are of the variety we call exponential growth, okay? And what's required there is that the base be greater than 1. It certainly can't equal 1. And as we saw with the pictures, okay, x can take on every conceivable value, okay? Every conceivable value here, all right? So the domain is positive, but our graph suggested that the range was only uh, the range was only positive values, okay? So here's some of the graphs we looked at, okay? And these indicate those things. The domain taken on every value of x, the range, okay, only the positive values. We have an intercept, all of them intercepting here at 1, okay? If you're after, we're trying to play name that graph, which is which here. Well, what we saw was when the base values get larger, the graph just would rise more steeply. So the one rising most steeply here is in blue, and that's probably 3 to the x. Okay, the one rising not as steeply, not growing, not with the largest rate of change. Okay, would be 2 to the x. Okay, and then 1.5, 3/2 to the x would be the red one in between. Okay, so what we say is they're always on the increase. Very simple. I mean, as compared to some of the rational polynomial functions we looked at. Find the intercept, okay, which is 1. Find the asymptote. Pretty much it, okay? Now, we said there's exponential growth, okay? And what we'll find in our applications is a lot of things will grow exponentially like this, okay? We also have what we call exponential decay, all right? And to that extent, okay, we're restricting that our base be something between 0 and 1, okay? And what's going to happen on that front is, okay, uh, the graphs are going to look like this, okay? They're always going to be decreasing. Now, I actually want to take you back to the uh, Desmos and share this with you, okay? Uh, but here we go, okay? We're just going to see. One thing we note is that, well, they still have the intercept, the y intercept of 1, okay? But they're kind of flipped across the y-axis from the ones we saw previously. Well, in fact, they are, okay? Because if we were to let's look at this down here. Okay, y equals negative 2x, or y equals 2 to the negative x. I'm sorry, which we could say is, okay. If you think about the graphs we saw before, this should imply a flip across the y-axis. Okay, so replacing the x with a negative x is to imply a flip across the y-axis. Okay, and we could rewrite that as you see here as 2 to the negative first to the x power, and of course 2 to the negative first is the half, is 1/2. So this is 1/2 to the x. So we're going to find that when our bases are values between 0 and 1, values between 0 and 1, we're going to have this decay rate. We're going to have, okay, as x increases, the function is going to be decreasing. As x increases, the function is going to be decreasing, which is contrary to what we saw with the exponential growth equations. Okay, so we're going to put us on hold here for a minute. Okay, so now we're back to our Desmos graphs, and of course what we were looking at were exponential growth. Now I'm going to alter this now and look at what happens when the uh, the base is between, okay, 0 and 1. And here you can see that it is the graphs the likes of which we just looked at, okay? So here we are at 0.7 to the x power, 0.6 to the x power, 0.3 to the x power, 0.1 to the x power, okay? So, so you can see here that the flow is reoriented in much the same way as we just saw on the PowerPoint slide, okay? So with the bases being between 0 and 1, we've got exponential decay, which means, okay, we're riding the positive side of the x-axis as our asymptote. We're going through 1 on the y-axis, and then we're forever decreasing. That is, as x moves towards infinity, the function is moving towards 0. The limit as x approaches infinity is 0, okay, as opposed to exponential growth, which is quite the opposite, okay, uh, and is pretty much just a reflection across the y-axis of the exponential decay. So there are two branches of exponential functions: the growth functions, as we can see here, and the decay functions with the base values between 0 and 1. Now, you might ask, well, what about if the base is negative? Look, we don't get a graph. You should be able to uh, answer why the base cannot be negative, okay? So we'll never have to worry about the base being negative, all right, for our exponential functions. It will always be positive, okay? So taking you back a little bit right here onto what we were looking at, okay? We have the exponential growth functions, y equals a to the x, a greater than 1, okay? Always growing, always increasing in the positive x direction, going through 1. As the base gets larger, the rate of growth gets larger, the average rate of change, the same notion, okay? For exponential decay, opposite direction, always decreasing as x increases, okay? Uh, the restriction a between 0 and 1, domain and range are pretty much the same in either increasing or decreasing. Again, take note of how we can illustrate by reflections the relationship between exponential growth and decay. Okay? We'll be back with another video talking about basic translations on these functions.